Hi ladies and gentlemen, this is Ms. Skokin. We're back to Algebra 2 and we're taking a look at section 4-3, logarithmic functions. And we are going to start as we usually do with our warm-up. So let's take a look at these problems. And it says use mental math to evaluate. That really just means that you're going to not use a calculator. You're going to write it all out and do it analytically. And the other thing, in your notes you do not have number 5, so you can do number 5 or not do number 5 as you choose. Turn the video back on when you're ready to check your answers to the warm-up. Now, in order for you to be able to do these, you needed to remember that negative exponents mean that you are working with the reciprocal of the number that you're raising to the negative exponent. So 4 to the negative 3 really means 1/4 to the third power. And with our rational or fraction exponents, such as 16 to the 1/4, that really means the fourth root of 16. So you can rewrite it so that it's in radical form, or you can write it this way, either way. And you should think of it as doing a square root and then doing another square root so that you can get the fourth root. The other thing that you needed to remember for number 3 was place value. And if you have 10 to the negative 5 power, that means you have 4 zeros and a 1. And that's where your decimal is placed. If you have any trouble with any of these, you may need some review. This is some kind of review from Algebra 1. So make a note if you need some help, and we can talk about it in class or in extra help after school. The objectives for this section: write equivalent forms for exponential and logarithmic functions. That means we want to be able to very fluidly go back and forth between the two forms, kind of translate back and forth for our own convenience for problem solving. And then we also want to be able to write, evaluate, and graph logarithmic functions. We have some new vocabulary: logarithm, common logarithm, and logarithmic functions. We're going to see what those are in just a few minutes. Let's consider if we started out with $1, how many times would we need to double the $1 before we got to $8? Now, we can determine this a lot of different ways, but let's use an exponential equation to model this situation. And remember that the form is f of x is equal to a times b to the x power. That's the way we often see it, although not the only way. We'll be taking a look at that later on in this chapter. But 1 is our initial value. The number that we're starting with is $1. We're doubling, so our base is 2. We don't know how many times we're doubling, so our exponent is x, and the number that we want to end up with, or our final or terminating value, is $8. So we know, now you know the 1 doesn't do anything, so what we've really got is 2 to the x is equal to 8. We know that 2 cubed, or 2 to the third power, is equal to 8. So we know that we have to double 3 times in order to get $8. Now, sometimes we can do it this way, but sometimes we have a number that we can't very easily do, or it might be an expression. And so when we have an equation like this, where the variable is in the exponent, and that's what we're trying to solve for, we use logarithms. That is the operation that is used, is finding the logarithm, and the logarithm answer is actually the exponent. So what we're looking for is the exponent, and we use logarithms to get us there. In order to go back and forth between exponential form and logarithmic form, we need to see what the relationship is. So we have b to the x is equal to a. This is the exponential form. B is the base, x is the exponent, so far easy to remember, and the number that we end up with that we get when we raise b to the x power is a. A is going to end up being in our logarithmic form called the argument. So again, easy to remember, log base b, so b was the base in exponential, and it's the base in logarithmic form. And notice where the base ends up. It ends up in the subscript position to the right of the log. A is the argument, so that's the number that we're taking the log of. And the answer that we get from this logarithmic equation is x, or the exponent. So when you have a logarithmic equation, the number on the other side is the exponent that we had in the exponential form. And as always with both of these, b has to be positive and b cannot be equal to 1. If you're not entirely sure about this, don't worry about it yet. Just put a little post-it in your notes, and then remember that you may need to practice this, but we are going to look at a few examples, and we're going to be practicing going back and forth between the two forms. So just a reminder, when we read the exponential side, it's b to the x equals a, and when we read the logarithmic side, it's log base b of a is equal to x. A is the argument, b is the base, x is the exponent. Let's take a look at an example, and just so you know, the question, let's see, the second one, 2 to the 25 to the 1/2 power equals 5 is different in your notes. In your notes it reads 10 to the 0 power is equal to 1. So I apologize for the mismatch, but you're going to be, in this example, changing from exponential form to logarithmic form. This one is a little bit more intuitive than going in the other direction, but that's okay. You'll be experts before long. So what I'd like you to do is, using your little reminder where it shows the exponential form and the logarithmic form, b to the x is equal to a and log base b of a equals x, using that picture that we saw on the previous slide, you're going to be rewriting these exponential equations in logarithmic form. Turn the video back on when you are ready to check your answers. Okay, so you see 3 to the 5th equals 243, log base 3 of 243 equals what started out as our exponent 5. And check your answers on these. Pause the video if you need a little bit more time. Also, the one that we had started with, 10 to the 0 power is equal to 1, we would put that in logarithmic form as log base 10 of 1 is equal to 0. Now we're going to look at example 2, and this time we're converting from logarithmic to exponential form. So we're going to start out in logarithmic form, as you can see, and we're going to rewrite it, again, using that same relationship between exponential and logarithmic equations. We're going to rewrite and end up with an exponential form. This time, question C is different in your notes than it is in the slide, so don't worry about that. In your notes it says log base 8 of 64 is equal to 2, and I'll let you know what the answer is to that when you turn the video back on to check all of your answers to example 2. Hopefully you, again, were comfortable changing from logarithmic to exponential, making sure that each of the position places you refer back to. After you get used to it a little bit, you do have to memorize the relationship between exponential and logarithmic. You do have to memorize that, but after you get a few under your belt and you've practiced a little bit, it should get easier. Now, as promised, the one that you have in your notes, log base 8 of 64 is equal to 2, in exponential form, that should read 8 squared is equal to 64. Now we know that the logarithm ends up being an exponent, so the rules for exponents also apply to logarithms. And we have rules for logarithms that we learned in Algebra 1. When we raise any number to the first power, we end up with that same number again. The way that we would write that in logarithmic form is log base b of b is equal to 1. So any number raised to the first power is equal to the original number in logarithmic form, and then you can see an example here. And then if you take the logarithm of the number 1, you're always going to end up with 0, because any number raised to the 0 power, you end up with 1. So those are properties that we learned a long time ago, but this is how they apply to logarithms. We do have a few special logarithms, and the one that we use most frequently is the logarithm with base 10, and it's called the common logarithm. If you ever see a logarithmic problem that doesn't have a logarithm listed, it doesn't have a base listed for the logarithm, then that means that it's base 10. That's kind of like we don't write the coefficient of 1 to x, for example. We don't often write the base of 10 when we're using a common logarithm. We just leave it blank, and that's the assumption that it's always going to be the base 10 log. Example 3 says we're going to evaluate by using mental math. What that really means is by not using a calculator. So we're going to do it analytically. And I'm going to recommend that you do this in a very specific way. When you have something like this, log, and of course it's base 10, of 0.01, I'm going to ask you to set that equal to y. And then rewrite it in exponential form. When you rewrite it in exponential form, it's going to be a lot easier to translate into it's going to be very obvious, I should say, what the power should be. So let's just take a look at the first one together. Log of 0.01 is equal to y. That means 10 to the y power is equal to 0.01. And then you can rewrite the right-hand side, knowing it's 100th, as 10 to the negative 2. So that means 10 to the y is equal to 10 to the negative 2. So y then has to be equal to negative 2. That's what we were looking for to begin with. Now, knowing what you now know, I would like you to try the next one. Turn the video back on when you're ready to check your answer for log base 5 of 125. Remember, set that equal to y. And then think, what number do you need to raise 5 to get 125? So 3, of course, is the answer. We need to raise 5 to the third power to get 125. We've got one more to do. Again, set it equal to y, rewrite it in exponential form, and turn the video back on when you're ready to check your answer. Starting with the number 5, we need to raise that to the negative 1 power to end up with the reciprocal of 1/5. In the last section, we talked about inverse functions, and you may have realized, because we started with the exponential function and we rearranged it, that the logarithmic function is the inverse of the exponential function. So if you graph both of them, you'll see that they do have symmetry across the line y equals x, and their domains and ranges are reversed from one another. And that meets the criteria for inverse functions. So let's take a look at an example. We're going to use 5 x values, and you're going to create an xy table, meaning you're going to plug these different x's into your exponential function. You're going to build an xy table that way, and then you're going to reverse the x's and y's in a new xy table. You're going to graph the original function and then graph the inverse function. So here is your original xy table. I'd like you to turn the video off, pause it for a second so that you can get your work done up to this point with the xy table and the graph of the original function, the exponential function. And then turn the video back on when you're ready to look at the inverse xy table and the graph of the inverse along with the original function. Remember, the notation for the inverse is read f inverse of x, and in this case is equal to log base 1.25 of x. So we have our xy table, and we have both graphs, or both functions, graphed on the same xy plane, noticing the symmetry at y equals x, that invisible line here. We've got another example to work. Oh, and the domains and ranges are flip-flopped, as we said they would be. We have one more example. We're going to use the same xy or x input to the function. So create your xy table and your graph of the original function, and then turn the video back on to check that answer, and then we'll do the other part. Here's your xy table of the original function f of x. Here is the exponential decay. Turn the video off now and flip-flop your x's and y's using proper notation for your inverse function, which is going to be the logarithmic one, and then graph the inverse on the same coordinate plane. Okay, here you go, and again, hopefully you put everything in the right place in terms of your notation. F inverse of x is equal to log base 10 of x. You have your xy table and you have the two graphs, noticing again the symmetry at y equals x. The domains and ranges are flip-flopped, so make sure to jot down the domain and range of the inverse function, the logarithm. On your calculator you have a log key. That log key sometimes is used as it's an inverse key, y to the x, and the inverse of that is the logarithm. And just a reminder, when you use that key, it's specifically referring to log base 10. In example 5, we have a real-world application, and this is associated with the acidity of food. And in this case, we have a table that lists the hydrogen ion concentrations for 3 different food items. We want to find the pH of each, and of course the pH measures the acidity or the alkalinity of substances. So let's take a look at how we would do this. Starting with milk, the hydrogen ion concentration is this very small number, and it's in moles per liter. The way that we would write that is we have the equation for pH, and it's equal to the negative or the opposite of the log of the hydrogen ion concentration. So on our calculators we would use the negative symbol, press the log key, and put in this number that is the ion concentration, and that's going to give us this number 6.6 and change. So milk has the pH of about 6.6. Knowing what you now know of how to do this, follow the same format for tomatoes, and then turn the video back on to check your answer. Tomatoes have a pH of about 4.5. Now lemon juice. Turn the video off and back on when you're ready to check your answer. And lemon juice has a pH of about 2.2. That's it for this section. See you in the next one.